Oh good, you're back. I've been waiting here for hours. So let's look at the summary slide. We already looked at the autoionization of water. This at 25 degrees, I didn't mention that this is temperature dependent, but it is, has a value of 1 times 10 to the minus 14, which is very small, and this is the kW, it's just an equilibrium constant. Again, since this is liquid, it is basically just this relationship here. And then according to Le Chatelier's principle, if one goes up, the other one goes down, and vice versa. And so you can calculate the hydroxide concentration from the hydronium ion concentration. You can also calculate the pH. So we know that the pH is equal to the negative log of the hydronium ion concentration. There's also something called the pOH, and these all are in a relationship, right? So if you have a pH that's equal to, let's say, 12, then the pOH is equal to 2, okay? And so the relationship here is that the pOH plus the pH is equal to 14. So those two always add up to 14. There's another relationship between the Ka and the Kb and Kw, right? So the Ka times the Kb is always going to be equal to the Kw. Now that's specific for unique acids, right? So that's not interchangeable. But if we go back to the phosphoric acid example, right? So the first ionization constant here, Ka, of the first proton in phosphoric acid, which produces a conjugate base, if the conjugate base acts as an acid, if the conjugate base obviously acts as a base, this is not the reverse reaction, but in a way it is connected because it produces phosphoric acid, which is the origin of the proton in the first place. So the Kb for that is related to the Ka by that equation I just provided a minute ago, right? So the Ka times the Kb in this case equals Kw. So we can use that information and calculate the Kb for this reaction from the Ka. So that's also a very useful piece of information or an equation that you should remember. But once again, I'm going to give you all of those equations and constants. But you just need to know how to use them and understand the relationships, like this one right here, right? You need to understand the relationship between pH and hydroxide ion concentration. So if I ask you to calculate the pH of these solutions, and yes, I guess it's important to specify what temperature, that we can use Kw here, right? So, but all it is the negative log of the hydronium ion concentration. And so if I'm giving this to you straight, you just plug it into your calculator, the negative log of 1.8 times 10 to the minus 4, and that actually gives you a negative number, and since it's a negative log, you then get the result, and it is 3.74. So this one is easy. Now the second one, you can't just put in the negative log. If you do put the negative log in, the negative log of 1.3 times 10 to the minus 2, you get the pOH, and so the pOH is going to be 1.89. So that's one way to do it. You can then use the relationship that the pH and the pKa is equal to 14. So it's just 14 minus 1.89, and that would be equal to 12.11. So that's maybe the quickest way to do it, but you should be able to calculate the hydronium ion concentration by simply doing Kw over the hydroxide concentration. And so then that is 1.00 times 10 to the minus 14 divided by that 1.3 times 10 to the minus 2, which and all of these units are in molarity. And so this gives you a hydronium ion concentration of 7.7 times 10 to the minus 13. And then if you take the negative log of 7.7 times 10 to the minus 13, you get that 12.11, right? You should also probably realize that if you accidentally just take the negative log of the hydroxide ion concentration and you end up with a number that's less than 1, that would be an acidic solution, but this is clearly a basic solution, so you got to use those tricks. Anyway, this is pretty simple. I suggest that you figure out how to do this on your calculator. You know, maybe you have one of those wonderful calculators, or one of those. Either way, you need to figure out how your calculator works and how to use the hydronium ion concentration. Here's the problem, worked out very clean for you. I've got those uploaded, obviously. Moving on to the next slide, which is your turn. All right, so these questions are all asking for either the hydroxide concentration or the hydronium ion concentration, and they give you the other one. So that's basically this equation, but you should also be able to calculate the pH of any of those three. You probably don't need to practice 3 of each, but you know, learn your calculator. That's essentially the point of this slide. I could also ask you to calculate the hydronium ion concentration not based on the hydroxide ion concentration but the pH, and so sometimes that's referred to as the inverse log or the anti-log. And so again, you're gonna have to figure this out on your calculator, or the 10 to the x button, which if you're given a pH of 4.8 and you do 10 to the minus 4.8, that is going to give you the hydronium ion concentration. And so that's exactly what you would do. You would put the inverse negative log of 4.8 in there, and so that would give you hydronium ion concentration of 1.6 times 10 to the minus 5 m. And if I give you the hydroxide ion concentration, there's a couple ways you can do that. Now, if I'm asking for the hydroxide ion concentration, but giving you the pH, you can calculate the pOH and then do the inverse negative log. So let's do that first. So if you take 14 minus 3.5, you end up with a value for the pOH of 10.5, and if you take the inverse negative log of 10.5, this would be the hydroxide ion concentration, you get a value of, gotta look down here, 3.16 times 10 to the minus 11, or you could actually take the inverse negative log of 3.5, so minus 3.5. This will give you the hydronium ion concentration, and that's going to be, that is equal to 3.16 times 10 to the minus 4, and then kW divided by the hydronium ion concentration, which is equal to the hydroxide ion concentration, which is what I'm asking for, would then be equal to 3.16 times 10 to the minus 11. There is it. Just I want to point out that my slides have a typo. These numbers are incorrect on my slides, but here they are in my lecture, so you should be good to go. And so now we're going to step up a few things. Let's determine the hydronium ion concentration of a 0.100 molar HCN solution. So the problem here is that this is a weak acid, and therefore the concentration of H plus is not equal to the concentration of the initial solution. So if I make up a 0.1 solution of HCN, it's going to shift. All right, so it's going to shift to dissociate a little bit of H plus and a little bit of Cn minus. And we know that 1 mole of hydrogen cyanide is going to produce 1 mole of H plus. And so this is in a 1-to-1-to-1 relationship. But initially, we have none of that. And we don't know how much this breaks apart. We just know that this is going to change by a factor of x. And this is going to go up by a factor of x. And so is this. And these two are equal to because they're all 1-to-1. We also know the relationship here, Ka, of the concentration of the products and the reactants, and so we should be able to calculate the concentrations at equilibrium here, right? So we already saw those things. They're called ice tables, right? So now we know that Ka is equal to x squared divided by 0.100 minus x, and we are given Ka, so I know this is equal to 4.9 times 10 to the minus 10, and you can use the quadratic equation, or most of the time we can make an assumption that x is actually much smaller than the original concentration. So compared to 0.1, x is going to be super small, but still we need to know what x is so that we can calculate the pH of the hydronium ion concentration. So if this is negligible, it basically goes to 0. That makes our mathematics a lot easier, because all we have to do is then x is going to be equal to the square root of 4.9 times 10 to the minus 10 times the 0.100, which is equal to 7.0 times 10 to the minus 6. And you can see already this is 10 to the minus 6, this is 10 to the minus 2. It is going to be less than it's going to be negligible. But what we say is if the percent ionization is less than 5%, then we can justify that. So you should test that. So you take your percent dissociation is calculated by taking the 7.0 times 10 to the minus 6, and you divide it by the original concentration of your acid, which is 0.100 m, and you multiply that by 100. In this case, we actually get 0.007%, which is much smaller than 5%, so we don't have to use the quadratic equation. And situations where you might have to use the quadratic equation will be when your K is rather large, like 10 to the minus 2 or 10 to the minus 1, and your concentrations, original concentrations, are rather low. So if your original concentration is like 0.002 and your equilibrium constant is 0.01 or something like that, then chances are you probably have a dissociation that's much larger than 5%, and then you'll have to use the quadratic equation. But most of the time you can make this assumption that x is not infinitely, but negligibly small. And so here's that problem worked out. Again, we already looked at these ice tables, so you should have no trouble with it. All right, so following the next few lectures, we're just going to exclusively look at these kinds of ice tables again.